It's a great pleasure for me to introduce the keynote speaker, Professor Jason Lowe, OBE. He's a Principal Fellow and Head of Climate Services for Government at the Met Office and Chair in Interdisciplinary Climate Research at the Priestley Center of the University of Leeds. Jason has over 20 years of experience as a climate researcher and research leader, contributing to scientific journal publications on a diverse range of subjects relevant to both climate mitigation and adaptation. He leads the UKCP project, which developed innovative new climate scenarios for the UK, which are being used in the third National Adaptation Programme. Internationally, Jason has contributed to all three working groups of the IPCC, the Intergovernmental Panel on Climate Change, and many UN climate reports. He regularly provides advice to government and other stakeholders on climate viability and change. A recent focus has been to provide information and guidance on climate change to the finance sector, including the Climate Financial Risk Forum and the Bank of England. He also co-directs the projects to update the scientific report for the fourth National Climate Change Risk Assessment. So, Jason, over to you. Thank you.
Thanks. We have a clicker as well. Does the clicker work? Brilliant. So, just thinking of my starting point, I'm curious what you think about the level of future warming that we might experience. So before we get into the slides, if everybody could put up a hand. Yeah, everybody please. Right, if you think warming will be limited to 1.5, you can put your hand down. If not, keep your hand up. Okay, if you think warming will be limited to 2 degrees, and this is the global average warming at the end of the century, put your hand down, so 2 degrees. If you think warming will be limited to 2.5 degrees, put your hand down. Okay, 3 degrees. Oh, I'm seeing a wavering from David at the top. I'll go a bit further. I did this same exercise yesterday with a group of people focusing on climate security. I'll tell you at the end how far I got with them. So 4.5 degrees. Okay, we got up to 5 degrees. Any more? It's like a bidding session, isn't it? It's very similar results to yesterday. And it also ties in with a major UN report that was released yesterday, the UNEP Emissions Gap Report. That highlighted that as a global average, if we take current policies, we add them up, then the central estimate of warming is around 2.8 degrees C. We'll talk a little bit later about what might take that up or down. So what I'm going to talk about is very much the climate science, but also how that interacts with the finance sector and the energy sector. I'm going to start with that just to kind of set the scene. So if we're thinking of climate and finance, what does finance do? Well, there are direct emissions from the sector. There are emissions from investments. But there's also financing of the net zero transition, financing of adaptation, and other investments can have a major impact on vulnerability. So they all affect the climate system and the people who live in it. We look the other way, there'll be weather impacts on businesses, including business continuity. And I phrase that as weather impacts. Okay, we were talking climate at the start, but what is climate? Climate is really the future weather, or the present day weather, or the past weather. It's weather in whatever period you want to look. And that's important because we're not so interested in long-term means, we're interested in extremes. So weather impacts on business continuity, weather impacts on assets and investments. I spent a lot of time recently talking to the Building Society Association about how they're thinking about the impact on their mortgage portfolio and what they might do to reduce the risks around that by working with their customers. There's also the effect back onto climate policy and business. And so it's actually quite a complex system. If you doubt the numbers, there are a whole host of published information on the physical consequences of present-day extreme weather. This is one that focuses on the insurance sector from Gallagher Re. And just take a look at some of these numbers. So the big ones in particular are associated with the US, and this is from 2024. So if you, for instance, take hurricanes Helene and Milton, you can see numbers in terms of economic damage getting up towards 100 billion. Not all of that is insured, but even there we're talking about very high numbers. If we look in Europe and focus, for instance, on the flash flooding in Spain, the economic loss estimate for that was estimated at around $11 billion. You'll also see on here some emerging perils, some emerging hazards. So, for instance, wildfire is starting to appear. And I suspect when we get next year's version of this, we'll also see quite a big feature from the US wildfires. But you can see it here in South America. You can also see this one at the top left that's bringing in the effect of hail. And that really causes us to think from a climate perspective, how do we actually model those new types of hazard that are being considered from the finance sector? My personal involvement, so I got involved with the Climate Financial Risk Forum, and that's a group of people who take part voluntarily in a working group organised in the UK by the FCA and the PRA. And there are a set of working groups. One of those is focusing on adaptation. And so our challenge in that was to think about how can we better improve the information for adaptation. And we built up towards, this was last year's report. We've just released an update on it with extra information. But I'm showing last year's because one of the key findings was that although the finance sector does think about present-day risk, thinking about future risks, there's actually not as much capability as one might imagine. Where there is capability, it's being applied in very inconsistent ways. And so what we did in last year's report was we put forward this idea of a very simple risk framework, the ABC framework. And this involves really three scenarios of the future. Too many, and it won't be picked up. It'll be seen as too complex or too time-consuming. But for three, the idea is that we start in the middle with the B. What's the B for? That's the pathway you budget or build towards. So that you set to a current policy level. We think probably the best estimate of this, and we did a great deal of co-development with the group, but also pulled in a range of scientific literature, that at 2050, that's a pathway that goes roughly through 2 degrees. If we were to go out to the end of the century, then we'd be looking at a similar temperature to the one I mentioned earlier, around 2.5 to 3 degrees. So that's the one you actively plan towards. But what about either side of that? So we include an aiming scenario. That's where we hope the world will go. That's the lower end of the Paris Climate Agreement of 1.5 degrees. But it's also in here for a very special reason, that when we actually started looking within organisations, it's usually a very different team that thinks about physical risk than thinks about emission reduction and mitigation. And we realised if we give them different scenarios, they already don't talk to each other adequately. So the A scenario is not only where we'd like to aim in terms of a world to adapt to, it's also the world that many organisations are working towards in terms of their net zero policies. So it gives a common scenario across those different teams. And we also include this idea of a contingency scenario. And we're not suggesting you actively build towards that scenario, but you think about what options you might need and what you would need to do not to rule them out in case you bring them in later. And so the contingency scenario is at the higher end. We spent a long time discussing how high should one go. Anyone who wants to look that up, you'll find there's quite a lot of data behind it. So we worked with Nicola Ranger, who was at the time at the University of Oxford, now at LSE, and we assembled a database of different information sources, 100 plus on hazard, but also information on asset level information and vulnerability. But there are massive gaps in those data sources. On the left-hand side is the numerical version of those scenarios, and the really exciting bit underneath it is an attempt to say, in the UK, we can actually pull out from our climate models information. And this example is for a 2.5 degree future world. In the model, it happens around 2050, and this particular plot on the left, it's showing the warming event. So it goes above 40 degrees, which was the previous and standing record observed temperature, and it has many different characteristics in that the event is much more widespread. So this will be an event that the UK hasn't seen a direct analogue of. The time series is showing that particular summer. What you might notice there is that there's a very large number of days above 30 degrees. That's important because there are a whole series of triggers, thresholds, vulnerabilities that increase quite rapidly after 30 degrees, including in the transport and energy sector. So we can also do a similar level of thinking for the energy sector. So I put together some of the interactions. And we've got the climate system in the middle, because I'm a climate scientist. If you were doing this from a finance point of view, you put finance in the middle or energy in the middle. But for now, let's work around the outside. That's a picture of a gas power plant. Of course, that is still producing carbon dioxide emissions, so that's feeding into the climate system and it's driving further warming. Could you add carbon capture to that? That's a debate that might come up later in the day. The changing climate is going to affect demand, and whether we're thinking about reductions in heating demand or increases in cooling demand, factoring that into our thinking about energy becomes vital. Clearly, the climate system and how it changes affects how we think about renewables. That can include the selection of the type and the location. It can also involve thinking about interconnectors and what's happening in those countries around us. But it also relates in the shorter term to operation and maintenance. But there was an excellent paper not so long ago highlighting that actually it's variability we need to focus more on when it comes to renewables rather than the climate change signal, at least in the first instance. We go further out. I wanted to capture this category. I didn't know what to call it, so I'm going to call it technical challenges. And you can see a picture of a nuclear power station. I think that's Sizewell, and also an illustration of the potential move towards a hydrogen economy. And if we start with the nuclear power station, I remember doing some work many years ago in the Met Office that thought about, well, what about the cooling water for nuclear power stations? How will that be affected? So there is a direct impact, even when we're thinking of these power sectors that you think, okay, well, that's not really going to be connected into this debate. Hydrogen's a really interesting one. So on one side, there's been a lot of work, including authors at the University of Reading, thinking about the consequences of leakage and the impact on atmospheric chemistry. So it impacts on methane lifetimes, it impacts on tropospheric ozone, it impacts on stratospheric water vapor, and so does lead to a warming. And so thinking about hydrogen needs to come with thinking about leakage rates. But there's also an impact the other way, and there was an excellent report from the CS Now programme that looked at water availability across the UK as we go into the future. And that's incredibly important for hydrogen production. You need a very large amount of water to produce a significant amount of hydrogen. And thinking where in the UK you might be able to do that and how you might ensure that continuity of supply, as in the UK we move to warmer, wetter winters but hotter, drier summers. And then the one that's very much on my radar at the moment is the idea of resilience. Are the assets in the power sector resilient to high temperatures? Are they resilient to intense rainfall and flooding? Are they resilient to subsidence, for instance, linked to drought conditions? And I'd like to think climate science can help with all of those in some way, but it also contains uncertainties. To close the loop, I also wanted to add this diagram. And so we need to remember, and we'll see this throughout the day, that we shouldn't necessarily think of finance and climate separately from thinking of climate and energy. And the other ingredient is making sure we also think about the role of policy in this, which links to all of these categories: finance, climate, and energy. And so we end up with a very complex system with interesting emergent behaviour when you start to couple it together. So now let's actually move on to the climate science. And I want to start with the past. Plot on the left is one I often show in talks. It's the global average near-surface temperature change from pre-industrial times. There are several curves from different climate centres around the world, but they're in close agreement, especially from 1900 onwards. And that's important because it's illustrating our high degree of confidence in these temperature observations. You can see the upward trend, especially established from the 1970s. You can also see that around that trend is variability. And capturing that variability on the changing baseline is incredibly important for thinking about the impacts of climate change and the impacts on resilience. At the end of the curve, you can see the result from 2024, so the first calendar year in the record where that global mean warming exceeded 1.5 degrees. This year, be interesting, we'll see the WMO statement coming out imminently and telling us where we are this year. A single year above 1.5 degrees doesn't mean we've breached the lower Paris Accord guardrail of 1.5. Although that's not actually specified in the Paris text, it's generally taken to relate to longer-term averages of around 20 years. But there is a debate precisely what metric that should be, that the World Meteorological Organization is very much focused on. On the right-hand side, I wanted to put these pictures to remind us it's interesting from a policy perspective talking about global average temperatures, but where people live, where physical assets are, that happens locally. And much of the damage is associated with extremes. So I've got some plots here from around the world. For instance, the heat wave in the US in 2021, an unprecedented effect with a large area sitting under a heat dome for a considerable period of time. At the top, I'm illustrating intense rainfall leading to flooding, and we can see over large parts of the globe that a greater fraction of the total rainfall is falling in the most intense precipitation events, and that's leading to flooding, whether it's going into rivers and bursting their banks, whether it's going into surface water flooding. Drought, we expect to see a signal in drought, and we do at an increasing number of locations, but it's others that's still hidden by that variability, the wiggles in the curve. But we're starting to see a strong signal emerging, for instance, in southern Europe. And sea level rise, I've put that one in because not only are there major energy assets at coast and some very expensive property that many finance organizations invest in, but it also illustrates the idea that some metrics of climate we're seeing an acceleration in. So if we look at sea level rise around the UK, that's risen by about 20 centimetres since 1900. But 2/3 of that have happened over the past 30 years. And this idea of seeing an acceleration in many metrics is one that I think we need to focus a little bit more on than simply saying, has climate changed? We look to the future, and we start with looking at forecasts that try to capture that variability. And based on the latest estimates, WMO produced a report earlier in the year drawing on estimates from around the world. They're It's an estimate of there being around an 85% chance that we'll see at least another year above 1.5 degrees of warming over the next 5 years. But also, importantly, there's a 70% chance that the 5-year average will be above 1.5 degrees. So that is then starting to take us much closer to breaching the Paris guardrail. Those types of forecasts can also be incredibly useful locally, and it's worth having a look in this publication, but it provides information, for instance, on the state of the El Nino cycle, which has impacts, for instance, on UK weather at certain times of year, but also on the number of tropical cyclones that we see. We look further into the future. This is a plot that kind of relates to the question I asked at the start. So if we're looking further into the future, we don't know what the emissions are going to be. To some extent, you can think of that as a good thing, because it means we as a global society still have some agency in that. We're able to decide on what those future policies are and those future behaviours. But because we don't know, we can't produce a prediction, but we can produce projections. So on the left-hand side, this is based on data from the Intergovernmental Panel on Climate Change, their last assessment, IPCC AR6. And there's more than 1,000 lines on that plot on the left. And each one pictures a different future storyline in terms of changing global population, in terms of global wealth, in terms of trade, in terms of policy, in terms of consumer behaviours. And what we can do is we can look along each of those at the climate response. Colour-coded in green, those that limit warming to below 1.5 degrees with a greater than 50% chance at the end of the century. And you can see in all of those, there are very rapid reductions in the present day and the near future, and those are sustained for a long period of time. You can also see many of them go below zero, suggesting for that limit, not only do we need to reduce emissions, but we would also need to remove extra greenhouse gas from the atmosphere, for instance, through biofuels coupled with carbon capture and storage, or direct air capture technologies. And there are big uncertainties how quickly we can develop some of those technologies or scale up some of those technologies. And on the right-hand side, this is the temperature response from a middle-of-the-road climate model run with each of those emissions. And I've illustrated 3 cases. So you'll recognise the one in the middle with the yellow star. That's the current policy central estimates. So that's the 2.5 to 3 degrees, 2.8 in yesterday's UNEP gap report. If you take all of the announcements that nations have made, that regions have made, that companies have made, and add them up, that gives us an estimate that's a little below 2 degrees, around 1.9 degrees C by the end of the century. But we also can't rule out these backtracking scenarios. So for backtracking, what would happen? We'd fail to implement current policy, or maybe we would actually roll back on some of those policies. And I think if we think about the geopolitics of today, we can already see some of that rolling back in some parts of the world. So having a scenario that pictures how that might progress over time takes us up to this higher end of around 4 degrees as a central estimate. But with climate uncertainty factored into that, it could be somewhat higher. And for every fraction of a degree, there's the potential to increase impacts, but also the likelihood of large-scale Earth system changes, tipping points. So I wanted for the final part of my talk to move on from just saying, look, where are we, and what is the headline result, into thinking about, in climate science, how can we move from defining the problem? Nobody wants to stand and give a talk, and it's really full of gloom all the way through. And how can we turn that around? How can we say, well, climate science is now increasingly focused on being part of the solution. It's helping, it's trying to work with different sectors. And it's a really exciting time for climate researchers, actually, in terms of the toolkit that we have. I'm curious, actually, who in the room would identify as a climate researcher? How many do we have here? Okay, that's good. And knowing some of the hands that have gone up, I think it's also good as well that I think people from different disciplines are very much identifying as climate scientists. If I'd done this 5 years ago, I suspect the majority of hands going up would have been physical climate scientists. And so I think that in itself is progress, that we're taking a more interdisciplinary route. But let's have a look at some of the exciting views. So we've seen that observations are important. A couple of additional examples here. So from the National Climate Information Centre, the Met Office houses on the left-hand side for UK climate records. This is an output from HAD UK Grid. Or we move to the centre. This is a global data set looking at extremes. So these are essential, not only for baselining where we are, but also for evaluating our climate models and starting to constrain our climate models. The latest developments, data recovery is incredibly important, and there's a lot of that happening at the University of Reading. People like Ed Hawkins are recognising there's a lot of data that can be mined that hasn't yet been digitised, and pushing the record back so that we can look in more detail at some of those events becomes incredibly important. There's also more opportunistic observations, whether that's taking information from, well, an example I saw that I thought was really interesting was taking a CCTV camera that was capturing an ocean view and trying to use what it was seeing with a very clever AI interface to link it to wave state and to wind speed. If you think about EVs, many of them also have a function that is providing some sort of driver autonomy. The sensors that go with that will be an incredible source of weather and climate information if we can capture it. But there are still barriers to accessing some of this data. And again, we might want to think of how geopolitical changes might impact on some of our ability to collect additional data. Even if we have all of the observational data we could hope for, there's still a challenge in that we have a relatively short period in a non-stationary climate. And so one of the really exciting activities is being able to produce synthetic observations. And we can do this actually as a byproduct of seasonal and decadal forecasts. There are different variants on this technique at different climate research centres. The Met Office, we have an approach called Unseen. And there's an example of it here on the right-hand side. This is looking at wind drought over the North Sea. And the black dots are proxies for observations. The grey dots are pseudo-observations from a version of the climate model, so the same metric. And we've looked in particular at what's happening at the lower end, and we had a particular threshold that we defined. We've colour-coded the model ones in blue. You'll see actually there aren't as many observations down there as you might like, and actually the distribution that you obtain for those wind drought periods, it's actually quite distorted in that model period compared to the observations. But it's really important with this technique to always ask, are we seeing something that's unseen, or are we seeing something that's implausible? Is it unreal? And so the understanding of physically what's happening in the system becomes incredibly important. This is another area where AI is starting to offer promise, and in particular the use of, for instance, diffusion models to boost the size of model ensembles and the statistics is a really interesting avenue. We move forward in time and we think about this period from a few months ahead to a few years. We're in the regime now of decadal forecasting. So a number of centres around the world produce decadal forecasts. They try to latch on to those wiggles we saw on the observations and follow that forward in time. And they offer the potential for decision making on that period that many organisations, especially in the finance sector, are asking for, i.e. a few months to a few years ahead. But at the moment, I think there's a struggle to try to extract that level of skill and use it in decision making. There are attempts to do that. So there was a very good set of projects with the Copernicus Climate Service. One of those looked at energy, one of those looked at finance. Well worth looking that up. I think I put a link on the slide. And there's an EU project I'm involved with at the moment called Aspect. There is a case study in the finance sector trying to understand how we might better use decadal forecast information within decision making. We go further forward in time to the long term. Some of the exciting developments here are being able to run our global climate models that typically have a spatial detail of around 60 kilometers, but take those down to finer scales. And this is a study, again, I picked one that includes an input from University of Reading, because there's so much going on here. And it shows when you increase that spatial detail of the atmosphere and the ocean, you can get really quite a different response. And this particular modelling study showed a very different response for rainfall with implications for flooding over the UK. And the next IPCC assessment will be an opportunity to look at this in more detail for more model years and more models. It's not only global model spatial scale that's important, we're also looking at downscaling. So typically we take a global model and take the output from that and drive a much more detailed model. And those more detailed models have advanced massively over the past decade. Now we're able to take the models that until then we used for weather forecasting, so going down to a couple of kilometres spatial detail, and said instead of running them a few days ahead, why don't we run them for decades? And that's opened up an entire new avenue really in climate research. And it's important because it gives a better simulation of extremes. It gives a better simulation of the diurnal cycle, for instance, of convection. And it gives a better simulation of the interaction of the atmosphere with the land surface, including cities and including topography. And so it's opening up opportunities to really dig into some of the extremes and also provide useful information, for instance, on thunder and lightning and hail. And then really the final aspect I wanted to show of the work around climate science is thinking about amplifiers and surprises. And I'm sure at various times during the day, the idea of Earth system tipping points will emerge. So these are, for instance, in the IPCC definition, critical threshold beyond which a system reorganizes, often abruptly or irreversibility. And these have happened in the past. We can see this from paleo measurements. But I think it's important to also highlight that there are major gaps in our ability to quantify the likelihood of tipping elements. And you will see people coming up with new estimates that look very precise. I think it's important really to question those and say, has the science got to that bit, got to that point? But it's an area where we need to push the research forward. We also need to think about whether there's temporary resilience in the climate system. So if we were to overshoot our temperature profile but try to bring the temperature back down, whether we could avoid a tipping point, because it takes time for that tipping point to become embedded. For instance, if we were to look at the response of the large ice sheets. There's also improved understanding that will help us monitor this type of event and hopefully provide an early warning system. And then my final slide. I've talked about a lot of climate model results, but I've deliberately also brought in observations and I've referred to physical understanding. It's important to put climate models into context. And I've got two different plots here. The one on the left is from a study that says, hang on a minute, current climate models, many of them are too hot. If we look at that global average temperature, many of them are pulling us to the very high end and questions whether we should actually use those models. I don't think you can rule out those models when you compare against observations, but thinking about what that means for decision making becomes important. But you can go the other way. Here's a study that looks at how the difference between the median estimate and the extreme tails changes over time, so-called tail widening. And it looks to see whether models capture that. And you'll see there's a big red dot over Europe and the UK that suggests almost all of the models are underestimating that tail widening, which is important for extremes. So models do contain information that is useful. So they contain information that can aid decision making, but they also need to be used with caution and form part of that set of information. And that's where I'm going to stop.